Here are the notes for section 7.4, power. In this section, we're going to talk about two specific applications of power, human power, or the power of a machine, whether it's a biological or an actual machine. And then we're also going to talk about electric power and applications in the household. So what is power? Power is the rate at which work is done. That's one way to think about it. Or it could be the rate at which energy is consumed. Remember that work and energy are equivalent. They are conserved with each other, so those two ideas are related. The unit for power is the watt. And actually, I should have capitalized that. A watt is a joule per second. So power, if power is a rate, it's going to be either the work over time, or we can think of it as energy consumed over time. And then again, the units for that would be joule per second, which is a watt, named after another physicist. If I take the equation for power equals work over time, and if I substitute in my equation for work, and I'm actually I'm going to simplify this. I'm just going to use work equals force times distance and leave out the cosine of theta for right now. Then power equals force times distance over time. But what is distance over time? Distance over time is velocity. So another way that we can write the formula for power is to say that it's force times velocity. And what we see here is that when a force is applied at a faster speed, we get more power. When the same force is applied at a lesser speed, we get less power. Here's an example. An Olympic weightlifter breaks a world record for the clean and jerk by lifting 247 kilograms up 1 meter. He did this in 2.2 seconds. How powerful is the weightlifter? Okay, so power is going to be work over time, or force times distance over time. And in this case, the force is the force of gravity, so that's mg, and the distance is h. Now notice that's gravitational potential energy. That's where that work goes. It turns into gravitational potential energy of the object. Okay, so we've got 247 kilograms times 9.81 times 1 meter is how high the bar gets lifted. And then the time is 2.2 seconds. So I would plug this into my trusty calculator. 247 times 9.81 divided by 2.2. I get 1,101 watts. That's as much power as a microwave. Power is a really power shows is a really useful, let's see. Power is a really useful quantity when talking about appliances and electronics. We know it takes energy for those things to do work. When you read the label, they always give a quantity measured in watts rather than joules. This is because we want to know how much energy that appliance will use every second. So by measuring the energy used by the machine as a function of time, we can compare higher energy machines to lower energy machines. So let's do some examples here. You use a 40-watt light bulb for the entire month of April, day and night. How much energy did the light bulb use? Okay, so first of all, power is energy over time. And if I multiply both sides by time, what I get is that energy is equal to power times time. So that's important, an important rearrangement of the formula. So to figure out how much energy the light bulb used, I'm going to take the power and multiply by time. Let's figure out the time. The month of April is 30 days. And there are 24 hours in a day. And there are 60 minutes in an hour. And there are 60 seconds in a minute. So I'm going to multiply by the numerators and divide by the denominators here. Dividing by 1 doesn't change anything. So I'm going to take 30 times 24 times 60 times 60. And I get that the amount of time is 2,592,000 seconds. Okay, so now the energy is going to be the power, which was 40 watts. And remember that a watt is a joule per second, so that's 40 joules per second times the number of seconds, 2,592,000 seconds. So I'm going to multiply, and now I get 10 million, 103,680,000 joules of energy. That's a lot. Your electric company sends you a monthly bill informing you of the number of kilowatt hours of energy you have used that month. What is a kilowatt hour? Determine how many joules equals 1 kilowatt hour. Okay, so a kilowatt hour, which is abbreviated kWh, is literally a kilowatt times an hour. So a kilowatt is 1,000 watts, and an hour is 3,600 seconds. 1,000 watts is 1,000 joules per second. And when we take 1,000 joules per second times 3,600 seconds, we get 3,600,000 joules. That's what 1 kilowatt hour is. It's that many joules. And again, it's a little tricky because when we see watts, we want to think that this is power, but a kilowatt hour is a unit of energy. It's the units that the energy company uses to cost our energy consumption. So let me show you something here with the light bulb in the month of April. The month of April has 30 days. And there's 24 hours in a day. So if I multiply those two numbers together, 30 times 24 is 720 hours. So here's how the electric company does it. Instead of multiplying out this crazy number of joules, 100 million joules, pardon me. What they do is they measure it, and they measure the energy consumption in kilowatt hours. So we would take the 40-watt light bulb, and we would divide by 1,000, because there's 1,000 kilowatts in 1 watt. And that gives us 0.040 kilowatts. And then we would say that the energy consumed by that bulb would be the power rating in kilowatts, 0.040 kilowatts, times the number of hours we had it on, so times 720 hours. So 0.04 times 720 is 28.8 kilowatt hours. Again, that's kilowatts times hours. Now, if I take 28.8 kilowatt hours and I multiply by 3,600,000, guess what I get? I get this answer up here. And I should, because those things are equivalent. Okay, so let's explore this idea of the electric bills and electricity used in households. Why does the electric company bill you in kilowatt hours instead of joules? Beside the fact that they would get to write smaller numbers on your bill every month, it also allows them to quickly calculate how much energy you've used for a certain appliance. It allows you to calculate your energy consumption as well. Let's take the light bulb from exercise 2. You had to find the time the light bulb was on in seconds. If you measure it in kilowatt hours, you can just take the power rating in kilowatts and multiply by the number of hours it was on. So let me take an example with, let's do one more example of this. Let's say that I have, let's say I'm in my living room. And in my living room, I have 4 light bulbs. And they're LEDs. So there's something like 15 watt LEDs. So that's a total of 60 watts lighting my living room. In my living room, I have the lights on probably about 6 hours a day, and there's about 30 days in a month. So that's about 180 hours in a month. So for the 4 light bulbs in my living room, how many kilowatt hours do I use? What I do is I take 60 watts and I convert it to kilowatts. And to convert it to kilowatts, I divide by 1,000. So it's 0.060 kilowatts. Then I multiply that by 180 hours, and that's going to give me the kilowatt hours. So 0.060 times 180 means that I use 10.8 kilowatt hours of energy to light my living room every month. Okay, so let's try this. Assume the cost of energy in Madison is 20 cents per kilowatt hour. What is the cost of keeping the light bulbs on? So let's use this number that I used. So we've got 10.8 kilowatt hours of energy to light my living room. And we just figured out it costs, or I just told you it costs about 20 cents, 20 cents per kilowatt hour. So I'm going to take 10.8 times 0.2, and I get $2.16 to light my living room. That's not bad for the whole month. Now the trick is, in a typical household, we have lots of things on. Lots and lots and lots of things. And some things draw power all the time. Anything in your household that has a little green or red or blue light on all the time is always drawing power. And as we saw up here, let's see, 30 days, 24 hours a day is 720 hours. So it can add up really fast if it's on all the time. Now let's try to light that light bulb using energy from apples. Okay, an apple, this is kind of a goofy example, but it's kind of neat to think about. An apple is about 95 calories. Let's say we can get all of those calories and convert them into joules. So we've got a 95 calorie apple, and 1 calorie is 4.184 joules. So if I multiply 95 times 4.184, the apple could potentially give me 397 joules of energy. Okay. 397 joules of energy is how many kilowatt hours? Let's see. We know that 1 kilowatt hour is 3,600,000 joules. So I'm going to divide. So this apple is only going to provide us with 0.00011 kilowatt hours of energy. Oof. Let's figure out how many apples that's going to take. So I need I'm going back up here, I need 10.8 kilowatt hours. 1 apple is 0.00011 kilowatt hours. So I'm going to divide 10.8 divided by that number. And I get, oh my gosh, 97,816 apples. And if each apple is $1 each, that is a lot of money. We are lucky that we're not We're not lighting our homes with apples. Okay, what about batteries? Would that be cheaper? Let's use C batteries. This 4-pack of C batteries is $7. Each battery has about 34,400 joules of energy in it. How much money does it cost to keep the light bulb on using batteries? Okay, well let's do our kilowatt hours again. Let's see, we want to keep the light on all month. So we need 10.8 kilowatt hours of energy. I'm going to convert that to joules. So am I going to convert that to joules? Yes. So this is 1 kilowatt hour is 3,600,000 joules of energy that I need. The batteries have 34,400 joules of energy per battery. And the batteries, well, 4 batteries cost $7. So when I'm setting this up, what I'm doing is looking to get things to cancel. I'm getting, this is called dimensional analysis. Kilowatt hours is going to cancel, joules is going to cancel, batteries is going to cancel, and I'm going to end up with money, which is what I want. I'm going to multiply the things on the top and divide by what's on the bottom. So to solve this, I'm going to take 10.8 times 3,600,000 times 7 over 1 times 34,400 times 4. Okay, so I got $1,978. That's quite a bit cheaper, but it's still not nearly as cheap as what the power company delivers to us through the electric lines.